Okay, to finish up our chapter on organic analysis, we're going to talk about what we actually do. Okay, chemists get to a point where they cannot use one of these things to give them all the information about a molecule. What we do is we combine certain results from these. So here I've just put a diagram that I put in earlier, but I've just kept the what it finds out. Okay, so we're going to use different ones of these, and the HSC could give you 2 or 3 different ones of these to help you identify the one molecule. Okay, so what have I said here? There's no current technology that allows chemists to take one photo of a molecule, or you can't just use one analysis technique to give me the molecular formula, the bonding arrangement, and exactly what functional groups are there in one simple test. We don't have it yet. So we rely on information from multiple tests of these instruments to identify an unknown structure, or to confirm, not conform, confirm that we have made what we're aiming for. Okay, that's usually what it's used for. One thing here is to consider is some techniques give us a molecular formula, and we haven't really talked about those techniques, but sometimes when you come to do a HSC problem, they might say, here's a molecular formula, here is, let's say, a mass spectrum, and here is an IR. What is the molecule? Okay, so from a molecular formula, you can get quite a decent amount of information, and sometimes we call that the degree of unsaturation. And I haven't got too much into detail in this. You will if you go into university chemistry. I've just kind of kept it simple, and it's going back to remembering our general formulas. And it's going back to, remember, alkanes have the general formula of CnH2n plus 2, okay? And alkenes, you're taking away, so that's your fully saturated molecule. If you just have one alkene or one double bond, remember that you've got 2 hydrogens coming away. Sometimes we call that 1 degree of unsaturation. That's a bit of extension, okay? But remember that alkenes have the CnH2n, and if you put a triple bond in there, you've just the one of them though, you've got the CnH2n minus 2, okay? So that's taking away 2 degrees of unsaturation, or I shouldn't say that, I should say adding on 2 degrees of unsaturation. Cycloalkanes, remember, if you get a cycle in there, you're eliminating 2 possible places where a carbon-hydrogen bond could be, if you're looking at the equivalent alkane. So it fits the same as the alkene. So you can look at a formula given to you and you can see which rule it fits, and you can kind of guess, it could be this or it could be that. Okay? So these are only simple scenarios, but remember, we're only likely to get simple scenarios in our exam. Okay? As a more general rule, you can look up the degree of unsaturation. I wouldn't suggest that you go into it though, okay? Alright, so when looking at a molecular formula, he's just going a little bit deeper. If you have a halogen on there, just assume it bonds exactly like a hydrogen. It forms a singular bond in there. So think of it's just taking the place of a hydrogen, okay? So, for example, my C4H9Br, if I'm counting the Br to bond exactly like a hydrogen, I can think of the molecule as like a C4H10. And that fits the CnH2n plus 2 rule. So I know just from that formula that I've got a saturated alkane with 1 bromine on there. So it's a halo alkane. So I know I don't have any double bonds there at all, okay? I just need to find out where the bromo is, okay? And we'll use different techniques to do that. Probably NMR would be best for that. Okay, if you have an oxygen in the molecule, there's 2 things that could happen, okay? If you have a molecular formula with an oxygen in there and the carbons and hydrogens still fit the CnH2n plus 2 rule, you have an alcohol, okay? Because remember, an alcohol, you can think of an alcohol as just pushing the hydrogen, the carbon-hydrogen, it's just kind of like inserting the oxygen into the carbon-hydrogen bond, okay? It's still going to fit the CnH2n plus 2 rule, okay? If it fits the CnH2n rule, It could be you've got a carbonyl or a carbon-oxygen double bond, okay? It could also be that you've got an alcohol with a carbon-carbon double bond, but I don't think they're going to be that nasty to you, okay? So if you've got an oxygen in the formula that fits the CnH2n rule, more than likely you've got a carbonyl there, and hopefully you'll have something to confirm that, like an IR spectrum, and you'll see that deep carbonyl absorption peak. If you've got nitrogen, things get a bit more complicated here, okay? Oh, I haven't fixed up my formatting there. I don't think they're going to throw one at you, okay? So here I've just presented the information to help you out, okay? So if you got CnH2n plus 2, you've got a saturated alkane, okay? If you got plus 3, you could have an amine. I don't think they're going to throw it at you. If you've got 2 less, so CnH2n, you've either got a double bond or one cyclic molecule, okay? Either or. If you've got CnH2n plus 2, you've got some options here. You could have one triple bond, or you could have 2 double bonds, or you could have 2 cyclics, or you could have one cyclic and one double bond. It gets a bit confusing with all those possibilities. I don't think they'll give you one, okay? So that's one thing you can do. So here I'm just moving on and looking at examples of where we combine more than one information or analysis technique. So you can see this question. I don't know what year it's from. I should have written that down. But what they've got is, you can see I've got a mass spectrum and I've got an IR spectrum. And I'm guessing that they're going to ask me what the molecule is. Okay. The following data were obtained for an organic compound words. It has carbon, hydrogen, and oxygen. Okay, it's got those 3 in there. It's giving you some more information. The compound is colorless liquid. Most organics are. That's not really helping. And it reacts with sodium carbonate powder to produce bubbles. That is a huge clue. I love that clue. Okay, so they've given you a word clue here. Sodium carbonate powder. So it reacts with the carbonate to produce bubbles or carbon dioxide. So we've got an acid, okay? If we've got an acid with carbon, hydrogen, and oxygen, we've got an organic acid. And we've got a carboxylic acid. So they're telling us it's a carboxylic acid, okay? I'm going to jump down to the IR spectrum, because if I'm now suspecting that we have an carboxylic acid, what I should see in IR spectrum is a wide and deep OH peak, yep, and a very deep and narrow carbonyl peak, and we've got that. So that is a OH, wide OH, so it equals carboxylic acid. And this is your carbonyl stretch, so it's even confirming more. So the IR spectrum, I've extracted all the information from it, but it's kind of given to me in the question. They've given you some redundancy, which is good to make it easier. So I've got a carboxylic acid. I know that much now. I'm going to go up to the mass spectrum, okay? I could go in a huge amount of details here, but I'm going to start at the parent peak, which is 74 here. I know I've got a touch at 75, but that's just for some isotopes of carbon, hydrogen, and oxygen there. They've labelled the 74 there too. They haven't labelled the 75, so that's another clue. So I've got a carboxylic acid with a molar mass of 75, oh sorry, not 75, 74 grams per mole, okay? You just need to work out what it is from here. So it's got a head of this, okay? So let's just work out the mass of this. So we've got 12 for the carbon, plus 2 oxygens, which is 16 each, so it's 32, and plus the hydrogen, plus 1, so 12 plus 32 plus 1 equals 45. Okay, so whatever's coming off it is the 74 minus 45. 74 minus 45 equals 29. Okay, there's nothing else here except a carbon chain of 29. Okay, 12 Okay, I put one carbon in, 12, one hydrogen, 13, one hydrogen, 14, 14, plus another carbon is 26, 27, 28, 29. All right. So let's just check. Let's go. I've got 3 carbons. I have got 2 oxygens and 1, 2, 3, 4, 5, 6 hydrogens. Let's just go, put it in our calculator, make 100% sure. 3 times 12 for the carbon, plus 2 times 16 for the oxygen, plus 6 times 1 gives us 74. So what molecule do we have? This here is propanoic acid. That took me too long. So they've given us a mass spectrum and an IR spectrum for propanoic acid. All right. Here's another past example. So the molecular structure of the medication paracetamol is shown below. So this, it's quite complex, isn't it? The first structure is in label. The second structure highlights 5 different areas of the molecule A1 through A5. Okay. 3 peaks of the infrared spectrum are labeled below. Which of the area molecules is B1? Ah, okay. So B1 is a very tight peak. It would just be. It's a very tight peak at about 30. It's not the alcohol peak, is it? So let's go to our. This is the one we want, the IR one. It's a very tight peak. It's looking 33 to 35. It could be an amine. Let's just make sure. 33 to 35. Yeah, that's looking pretty good. So it's looking like an amine. Do we have an amine on here? Yes, we have this amine. So it's A3. Okay. So question 18, the carbon-13 NMR spectrum for paracetamol is shown. Okay, we've got certain peaks or certain carbon environments there. Which of the areas of the molecule corresponds to the peaks in the graph above? What are they asking there? Which of the areas of the molecule correspond to the peaks in the graph above? Well, haven't we've got differing carbon environments there. Because, I mean, look at how many carbon environments there are. We've got this one, then this one, and then, all right, we've got 1, 2, because this is lopsided too, I think all of these, 1, 2, 3, 4, 5, it's 8, but 1, 2, 3, 4, we've got 5, so some of them must be the same. I'm a bit stuck here because which one in particular? Okay, which of the following areas of the molecule corresponds to the peaks in the graph above? Okay, so they haven't shown all peaks. That's a bit confusing there. They've got 1, 2, 3, 4, 5. I'm going to assume, with my knowledge there, what we need to do is go back to our carbon-13 NMR data, that data on our data sheet. It's going to be, I'm guessing it's what region of the molecule. Have we gone too far? Yeah, we've gone too far. Where's our data sheet? Have I done it here? Didn't I paste it in? Oh, what a duffer. Alright. I can't find it here and it's making this video even more boring than what it already is. Okay. I haven't got a data sheet in front of me, but I'm using an educated guess here. I need to go right back down, don't I? Okay. I'm going to guess what area of the molecule has 1, 2, 3, 4, 5. I'm going to say it's A2. Okay. it's talking about the that benzene ring there. Alright, that was a bit harder. So, 2 activities. I've got this practical matching structures, and I've got some chemical sleuthing, which is kind of like this one, but with a formula, and then I take the formula away. Have fun with those. Hopefully this video helped you out though.